Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve this plate with hole with hyperelastic material. Here I have taken Mooney Rivlin material model. Our geometry is a rectangular plate with hole at the center of a radius 1 meter. Now we'll see the material model. So in hyperelastic material model, we have to specify the constant. One is C10, C01 and D1 is a compressibility modulus and Poisson ratio. We should not specify the Poisson ratio of 0.5, it should be very close to 0.5. So I have taken 0.4995, we can take 0.49 also. In code aster, if you want to take hyperelastic Mooney Rivlin material model, we have to specify two constants. One is C10 and C01. C20 is 0. If you are using a signorin means we have to specify all the constant. Now we are solving Mooney Rivlin material model. And boundary conditions. Left side I am going to fix it and right side I am going to apply a displacement of 5 meter. Now we will solve this case, hyperelastic model case using salome. Now I have opened here, just go to geometry model. There are different ways we can model this geometry using 2D sketch also. Now I am going to use simple cube box construction. The x length is 10 meter and y height is 5 meter. The thickness is 1 meter. This one is 10, y is 5 and thickness is 1. Now we can use this fit screen option to view our geometry. Now it is correct. Just apply and close it. Now we just want to create a hole at the center. For that I am going to use option called create a cylinder. The first option, OZ, the radius of the cylinder is 1 meter and height also 1 meter. Now you can see the cylinder is creating at the origin. Then we will translate the cylinder. Just apply and close. Now select the cylinder 1, go to operation, transformation, translation. The total length of the plate is 10 meter. I just want to move it into 5 meter at the center. Height is 5 meter. Just move it into 2.5. Now I have created this. Now just apply and close. Now you can see it. Now we'll cut this cylinder from the plate using Boolean operation. Go to operation, Boolean. There is option called cut. The main object is box 1, tool object is translation 1. Just apply and close. Now you can see, now we have created our geometry. Then we'll create a groups to apply the boundary conditions. So select this cut one. Before that we'll save this geometry. Go to file, save as. Just navigate the folder where you want to save it. I'm just want to save it in the code aster folder. Mooney Rivlin, I'm just saving here. Now we'll create a groups to apply the boundary conditions. First I just want to create a group of face group, left side. Here I just want to fix it. I'm just naming as fix, just apply it. Right side I just want to apply this displacement. Just select this face, add it. Here displacement. Now just apply. Now we'll create one volume groups also. Select all, we have only one volume. I'm just naming as V1. Just apply and close. Now you can see it here. Fix, displacement and total volumes. Now we'll save this file. Now we have completed the geometry model and creating groups. Now we'll move into meshing to create the mesh. Now select this cut one, go to mesh, create mesh. For this case, I'm going to create a simple text element using NetGen 1D, 2D, 3D algorithm using simple 3D parameter. Here I'm just going to give size of 0.3. Just say OK. Just apply and close. Just right click this mesh one, compute. Now we have done this. Just save it. Here we just want to fix it. Here you can see Similarly, here we just want to apply the displacement. This is complete volume. Okay, so before going for creating the setup, just check the groups. Now we have checked it. Now we'll move into aster study to create the setup for FEA. Just table, just say OK. So first go to add study. First we'll read the mesh. This is our mesh in MED format. Just apply and OK. Now we have read it. Go to model. This is a 3D model. Everywhere we can use mechanic 3D model. Just say OK. Just apply and OK. Then go to material. So first we need to define a material. Previously we have used the linear isotropic material for linear elastic problems. For hardening problem we have used traction and traction command we have used. This one we have used, and acroline for to specify the tangent modulus we have used. For this hyperelastic material we have to choose the option called Elas hyper. Here you can see Elas hyper. So this is the command to specify the hyperelastic material constants. Just go to edit. So in this exactly one we have to specify. One is Poisson ratio. I am going to specify it 0.4995 and C10 constant. Now we will take the material value of C10 constant is 1.751 and C01 constant value is 4.625 e power minus 2. 4.625 e minus 2. C20 is 0. Density need not to specify, it's not necessary. Anyway, I'm just specifying 7870. Now save OK. Just apply and save OK. Just save it. Now we'll assign a material. Mesh and model. Edit. We'll assign a material to everywhere. Just material. Just say OK. Just apply and OK. Now we have assigned the material. Then we'll create a function, a load function. There is an option called define function. Coordinate. Here choose time. Edit. When time is 0, the load multiplication factor is 0. When time is 1, the load multiplication factor is 1. So this is the way I'm going to apply the load. Just say OK. Just apply. This is I'm going to name it as load multiplication factor. Just apply it. Save OK. Now it is done. Now just go to assign a mechanical load. Here I just want to fix it. Edit. Group of element. Just edit it. Choose the fix. Just say OK. Blockage. Displacement. I'm just fixing the left side. It will fix all the displacement dx, dy, dz 0. That is direct command. Just apply it. One more thing is just go to edit. Group of element. Displacement. Just say OK. Instead of blockage, we have to apply the displacement of 5 meter. Just specify dx as 5. Just say OK. Just say OK and apply it. Now we have defined the fixed and load boundary condition. Now we'll move into time step defining. Yes, you just go to function again. Here go to defi list real 0, edit. Up to 1 we just want to solve it, and pause. I'm just making step length is 0.1. There are 10 iterations it will do. just say OK, just apply and OK. So then we have to define instant. The method is auto method. Edit, choose time step list as listdr, just apply and OK. Now we have defined load multiplication function as well as time period to solve. Then we have defined the load also. Now we'll go for solver, static nonlinear solver. Just say OK. Here there is option loads, just edit it, choose this one, and load multiplication is load f. Just say OK. Now there is option called comportment. Edit. Here we have to choose the proper relation and deformation. Instead of elastic, we have to choose elas hyper for hyperelastic material. Instead of petit, we have to choose grad GDP to predict the large deformation as well as the rotation. So this is, we have to choose it. Just we can choose the element group also. Anyway, we have only single element, it will apply to all. Just say OK, just apply it, save OK. Now go to post processing, call champ. So now we'll reuse the input object. Now constraint and deformation criteria. In constraint, first we have to calculate a sigma int element, then sigma int node. Then deformation, EPSI int element and EPSI in node. Then criteria, SIEQ element and SIEQ node. Just apply it, just say OK. Then finally we have to save the output in RMID format. Go to output, there is an option called set output results. So just navigate the folder where you want to save the output file. I just want to save it in the same folder, pictures, code aster. Mooney Rivlin. Here I just name it as result.rmid. Just save it. Here we have to choose edit mesh. In results we have to choose call champ. There is an option called tout champ, make it yes. Just say OK. In MID format, just apply and OK. Now we have created a complete setup to solve the hyperelastic case. Now we'll solve this case. If any error comes, we have to view in the message file. From that we have to check the material property and boundary conditions. Now I'm just giving some more memory to solve it. So just click it, 5 seconds, just run it. Now you can see it here. It has solved 7th iteration of 0.7. Now it is solved completely without any error. Here you can see diagnostic job is OK. Now we'll go for paraview to do the post processing. Just go to paravis. Just right click and open. Pictures, code aster, Mooney Rivlin. So this is our result file. Just select and OK. Just apply it. Now we have imported the output file. Now just go here, displacement, just run this case. Initially it will show everything is 0. Now again move into strain. Now see, just run it again. Now go to Van Mises stress, just run this also. Again change this into directional stress, run this completely. Now we'll move into first one, displacement. So initially we have to read complete data. It takes some time to read the data. So instead we can go for this option, just apply it, just run it, just move into strain. This one is the x directional strain, this one is the von Mises stress, and finally this is the directional stress data. This one is the sigma x, sigma yy, sigma zz. Now we'll change this color to view the results. So use this one, rainbow, blue to red, just apply and close. Just edit, here just choose 12. Okay. Similarly for epsilon also, this is the strain data. Change this also into rainbow, just apply and close, make it this into 12. Again here also von Mises stress, change this also into blue to red, just apply and close, make it this value into 12. Finally this also. Now this one is the displacement. Now we'll animate it. So here we cannot see the deformed shape. For to view the deformed shape, just go wrap by vector, just apply it. So this is the deformation. This much it's getting elongation is happening. Now similarly strain also we can view it. This one is the x directional strain, and for von Mises stress, so maximum stress is coming around 15 Pascal. Now we'll plot stress strain curve using an option called plot. Just enter a plot in this search option. Here you can see in plot there is an option called plot data over time. Just select and enter it. Now we have to choose the nodes. I'm just choosing here. Just apply it. Now it is plotted. Now just move into plot data over a time. First we'll check the displacement and tick all. Choose the x directional displacement and scroll down here. There is an option called average, medium or minimum. Choose maximum. Here you can see this is the displacement we are applying in one direction, in x direction. When time is 0, the displacement is 0. When time is 1, the maximum displacement 5 we are applying. Now our displacement is correct. Now we'll plot stress strain curve. So x data is a strain. We have to choose. Just make it x directional strain, and this is, you just make it stress. I'm just choosing a von Mises stress to plot. Von Mises stress to fit the graph. Just click this one. Now you can see this is the stress strain curve for hyperelastic material. Now we have taken a rubber and Mooney Rivlin material model. So now we have completed solving a Mooney Rivlin hyperelastic material model using code aster. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.